Well, good morning. This video now will be about Tim's notes and how he develops free-fall, and also a couple of his techniques about how to solve basic problems involving equations, which I think is very valid, especially if you have trouble choosing the right equation, knowing how to find a solution. So I'm going to ask you guys to pause the video now and make sure that you get Tim's PowerPoint. I gave you this, was the first handout I gave you about this topic, and be ready to follow and start on this picture of the Leaning Tower of Pisa. So now that you're ready to go, let's move on. Tim is going to make up some experimental made up data for the free fall, and I just want you guys to see the process. So he's describing right now on his notes the acceleration of free fall and Galileo's experience, and basically he's showing here the idea of an apple, okay, on free fall, and he's showing the feather on the side just to make sure that you guys get the idea of the free fall. And so there is a multi-exposure of the image of the apple and the feather as they are falling in a partial vacuum. So I guess here on the top of the picture we have the opening to release the system, and this now is a vacuum chamber. And then we have the apple falling, and just want to choose a spot on the apple, so it's going to be a bottom of the apple, to set the heights of the apple and the feather. So there we have the apple and the feather, okay, moving down, and we need to scale this. So to scale, he's saying that the apple is 8 centimeters wide. You guys can see that. So he's saying that that's 8 centimeters wide, and now he's going to put a little meter stick down so we can measure the position of the apple for successive time intervals. Okay, so that would be a 0, and then about -9, a bit more than an apple, -22 centimeters, -37, -55 centimeters. Notice that what he's doing here is setting a reference frame that is 0 at the point where the apple is being first observed, and positive vertical up. Okay, that's what he's doing, which is not mandatory, but is the most common thing that people do. Now we need to find the time. So he's going to suppose that the time between two images is 0.56 seconds, and with this you can make a data table using the raw data. So he's using y, he's calling the vertical coordinate y, which is a traditional way of calling the vertical coordinate, and then the times would just be 0.056, adding the first time is 0, 0. Now we need to calculate delta t, delta y to find the velocity of the apple. So to find those things, notice that the delta t, you're going to subtract the t that you have minus the first one. Therefore, the first delta t is blank because you don't have a second one. Same thing for the first delta y, and same idea for the first v. Now, moving forward, to calculate my delta t, you're going to subtract the current t minus the previous one. So that is the current minus the previous one. Then you move down, so now is the third time minus the second time. Then he's doing the fourth time minus the third time. And then he's doing the fifth time minus the fourth time. Okay, notice he is doing something different than what we did when we were studying proportions, because what he's doing is just preparing to be able to tell you guys the time between consecutive observations, time, and also displacement of those consecutive observations, and then he's going to take the ratio to find the average velocity between these two. Okay, so now let's go for the delta y. So the first delta y is going to be -9 minus 0, so that is -9. The next delta y is -22 minus 9, and that is -13 centimeters. The third delta y is -37 minus 22, which is going to be -15 centimeters. And then the next one is going to be -55 minus 37, which is -18 centimeters. And then we have our delta y's in there. To find now the velocity, you're going to divide delta y by delta t. So the first one is -161. The next one is going to be -232 according to Tim. I have not done any of these calculations. The third one is -268. and then the fourth one is going to be negative 321. Two things that I would like to note in here, and let me see if I can actually bring my computer, screen. Yes, I want a white screen. So two things. Number one, the units on the table are missing. So the units for delta t would be seconds. The units for delta y would be centimeters. And the units for v right now are centimeters per second. Now, another thing that I wanted to mention is this. When Tim was doing his calculation, velocity equals delta y over delta t, what he was finding was actually the average velocity. The only thing is that we are assuming that delta t is relatively small. So if delta t actually approaches 0, then v average kind of approaches v instantaneous. And then that's what he's calling his velocity. So now let's just unwhite the screen and go back to the normal progression of the PowerPoint. Screen here, unwhite screen, and then let's keep progressing. So the next step is going now to prepare a little graph of those average velocity values approximated to being the velocity values versus time. So here is the time axis, all of the time intervals. These are the velocities in centimeters per second. And now you're going to be plotting those points here, the negative 9 and, sorry, the 0.056 and negative 161. Okay, so we're going to plot these data points in here, and they will now just come into our data here, okay? And after doing this, now we're going to draw a trend line passing by those points, okay? And this is the best line that we can get. Moving forward, the graph is linear, and so the acceleration is a constant, but we had already established this. We had already talked about this on my own video from my own notes. The y-intercept, which is the initial velocity, is not 0. Well, is it a big deal? No, we just don't have all of the images of the apple. The apple starts falling before we start actually collecting data about it. So that's not really such a big deal. Okay? The acceleration is the slope of this graph, and if you do the acceleration, to find the slope, I'm going to do rise. On this case here, for the interval he got is 0.224, and then run, okay, for the range that he got is negative 220 centimeters per second, and then we get an average acceleration of negative 220 divided by 0.224, or negative 982 centimeters per second squared, which of course is a very perfect number, although I would expect a good result if we actually did this experiment. On the range of this apple moving, air resistance does not build up enough to be significant. Determining the acceleration of free fall experimentally. So let me just now move ahead here. That acceleration to gravity is going to be called g. And when he says that all objects accelerate at negative g, what he's assuming again is that he will always represent positive up, which is not necessary. It's just the most common way to do this. And then this acceleration to gravity in absolute value becomes 980 centimeters per second squared. If there is no air resistance or air resistance is negligible, okay, we're going to have that value for the acceleration due to gravity. And we usually round this number to 10 meters per second squared, okay, just because it makes our life a lot easier. He now has a link to go to the hammer and the feather video about the Apollo 15, but we saw this video on my own set of notes. So let's now move on. We are kind of done with the free fall idea. Now we're going to prepare to solve problems. So in general, okay, these are the equations that we have for constant acceleration motion. So this here is an equation for displacement versus time. The second equation is an equation for velocity versus time. The third equation, which is also known as, I never know exactly how to spell Torricelli, you know, Torricelli's equation, and is velocity as a function of displacement. And finally, this equation here is known as the average displacement, or something like this. This is the equation that I told you guys I've never used in my life, but the IBO has it, so I think it's important for you guys to have access. If it's free fall, I'm going to substitute g in every single acceleration, and usually we're going to also use delta y for s, or y for vertical position. Okay, now we're going to practice those kinematic equations. Okay, so now a little brainstorming about the 4 equations that we have, and let's see how we can actually solve some problems. So for the first problem, I just wanted you guys to see the whole idea. Okay, so how far Pinky and Brain will go in 30 seconds if their acceleration is 20 meters per second squared. So what do we know? We know the acceleration is 20 meters per second squared. That was given. We also know that the time is 30 seconds. That was also given. Now, we don't know the initial velocity. And so we're going to imagine, or it's implicit, that the initial velocity is 0. If they don't say anything, we just assume it's 0. And if we don't do that, there's no way we can actually solve the problem. Now, what do I want? I want to know how far, so I want to know the displacement. Okay? We have 3 equations we could use. So an equation for displacement, an equation for velocity, and Torricelli's equation. Now, I know time, so I don't know anything else. So let's just drop the equation that does not involve time, which is Torricelli's equation. Finally, I don't want to know velocity, I want to know displacement. And therefore, I can also drop the equation for velocity. And then I have one equation that involves what I know, time, and acceleration, and what I implied, initial velocity, with what I want, which is a displacement. So the solution now is just plug and chug, just plug in the numbers, and we get 9,000 meters. I hope you all understood this problem, and now let's move to the next one. There they are, traveling. And moving on to our next problem. So how fast will Pinky and the Brain be going at this instant? So how fast? Now they want to know the velocity. This is what I need to know now. So what do I know? I know again the initial acceleration. The acceleration to be 20 meters per second squared. Okay, that was given. I know time to be 30 seconds. That is also given. We are implying that the velocity, initial velocity, should be 0. Okay, and at this time I want to know the velocity of the object. The formulas I have again, the formula for displacement, the formula for the velocity, and Torricelli's equation. And just a little hint, time is not known. Time is known, so I can drop Torricelli's equation. I'm going to ask you guys now to pause the video for a little bit, and try to finish the problem on your own, and then come back to see my solution. Sorry, team's solution. So let's move forward with team's solution then. I want velocity, so I can also drop the equation for displacement. And then I have just one equation for velocity, that's going to involve what I know, acceleration, time, implied initial velocity, with what I want, which is the final velocity. So this now becomes again just a nice plug and chug. Okay, and you plug in the numbers and you get 600 meters per second. Hope you all are okay with this problem. And now let's get ready to move on to the next one. Moving forward. So how fast will Pinky and the Brain be going when they have traveled a total of 18,000 meters? So I want you guys now to actually identify what is known, okay, and what is wanted, and which equations you should use. Please pause the video for a couple minutes and try to find a solution. We'll be back shortly with Tim's solution. Well, I hope you all have actually now worked your own solutions. And so let's see here. What is known by us? That acceleration is 20 meters per second squared. Okay, that was given. We also know that the displacement is going to be 18,000 meters. This was also given. We are still implying that the initial velocity was 0. Okay, and I want to know the velocity after traveling 18,000 meters. Notice that the time is not going to be the same as before. I don't know time at this point. So I have my equation for displacement, I have my equation for velocity, and I also have my equation for Torricelli's equation. So I don't know time, so I need to drop the two equations that involve time in there. So I'm going to drop the velocity equation, and I'm going to drop the displacement equation. The only equation I have left over is Torricelli's equation, and then it's just a nice plug and chug. So I'm going to do v squared equals 0 squared, which is initial velocity, plus 2 times acceleration, 20 times 18,000, and that gives me then a velocity of 850 meters per second, which I hope you guys got it right. So now let's change a little bit and let's solve a couple problems involving free fall, I guess. So a ball is dropped off the Empire State Building, which is 381 meters tall. How fast is it going when it hits the ground? Notice that in free fall problems, often some information is not given because it's an assumption that you're going to know it by heart. As in, remember the properties that we discussed before? The acceleration to gravity is going to be 10 meters per second squared. If you toss the object up, the velocity at the highest point is going to be 0. The time to go up equals time to come down. And the velocity that you catch the object on your hand is equal and opposite to the launching velocity. So let's just see this here. There's animation of the ball falling. And I would give you guys now a couple minutes to list down what is known and find the formulas to solve the problem, and check back here once you have your solution. So I hope you have your solution, and let's see how you did. What do we know? That acceleration is acceleration to gravity, and that's going to be negative 10 meters per second squared. Okay, that's implicit, but we can also assume is almost a given. We know that the displacement is going to be negative 381 meters. Okay, that's the height of the building. And I'm also implying that the initial velocity is 0. If they don't say that I toss the object, then usually that means I'll have dropped. Notice that on Tim's solution, what he is doing is setting a reference frame with the 0, I don't know, maybe down here at the ground, and positive up. In that way, the acceleration due to gravity, g, is going to be negative 10 meters per second squared. And also, my delta y is going to be negative 381 meters. Okay? So what do I want to know is the velocity at the bottom. Okay, we have the three formulas. One formula for displacement and time, velocity and time, and Torricelli's equation. So since time is not known, drop the two equations that involve time, and then my solution becomes just plug and chug in Torricelli's equation. Negative 87 meters per second squared. I hope you guys got that one right. So let's now move on to the next problem. The ball is dropped again from the Empire State Building, 381 meters tall. How long does it take to reach the ground? Notice now that how long is actually a question of time. So I want to know the time to hit the ground. There's the ball dropping, and now let's just see. I would like you guys to again pause the video, try your solution, and then come back to check on Tim's solution. Okay, so now let's check on Tim's solution. Okay, what is known? We know the acceleration, or we imply the acceleration to be negative 10 meters per second squared. We know the displacement to be negative 381 meters. That's given. And we know that the initial velocity is 0, or that's implied. What we want at this point is time. That's my question. So the formulas will be S equals ut plus 1/2 of at squared. That's my equation for displacement. My equation for velocity, v equals u plus at. and then Torricelli's equation, v squared equals u squared plus 2as. Okay, since t is what I want, I need to drop the equation that does not have time. Okay, and he's dropping the second equation because this equation here involves velocity and time, and I don't know the velocity. Okay, I know the displacement. So I need to keep an equation that will involve displacement and time, which is this one here, the first equation. My solution now becomes just a nice plug and chug, and then the answer is 8.7 seconds. Moving now towards the next problem, let's change now to the cheerleader situation. Okay, so a cheerleader is thrown up an initial speed of 7 meters per second. How high does she go? Before you guys go into the solution, let's quickly remember that when an object is tossed vertically up, we talk about this, and I have already mentioned before, but just to make sure that we have all of this clear in mind, okay? If this object is tossed with a velocity v0, certain time later is going to be at a velocity v1. At the highest point, the velocity must be 0. When it passes by these little points here, the velocity is going to be the opposite of what it had before. Okay, so we have that the velocity coming back is the opposite of velocity going up. The velocity at the highest point must be 0. And we also have that time to go up equals time to come down. We addressed this on my own set of notes. So now that we've done this here, let's go back to the screen. Where is here? Screen. Unwhite the screen. And I'm going to ask you guys to pause the video, work the solution, and come back here and to see Tim's solution. Okay. So now that you guys have worked the problem, let's see Tim's solution here. Okay, so I'm implying that the acceleration is negative 10 meters per second squared. That the initial velocity is 7 meters per second, that is given, and that the velocity at the highest point is 0. I mean, that's implied, this is what I told you, that those are little details you need to know. And I want to know the displacement, the change in height. We have 3 equations, okay, and now let's see which equation we should choose. I don't know time, so I should drop the 2 equations that need time to be answered, and Torricelli's equation can be a good solution for us. So just now plug and chug. Notice that I'm plugging negative 0 for the final velocity because at the highest point, her velocity is going to be 0. Okay, and I'm also using negative 10 for the acceleration to gravity. So that means that Tim is still, as he implied at the beginning, selecting positive up. And then her maximum height becomes 2.45 meters. I hope you all got this one right. Moving forward, another problem. So a ball is thrown upward at 50 meters per second from the top of a 300-meter Millau viaduct, or something like that, the highest bridge in the world. How fast does it hit the ground? Again, how fast means velocity. Okay? So that's what he wants us to do. I'm going to ask you to pause your video for a couple minutes, work the solution, see what you get, and then come back here to see Tim's solution. Okay, so let's see Tim's solution for this problem. What do we know? We imply acceleration is negative 10 meters per second squared. Initial velocity is 50 meters per second. That's given. And that the total displacement is going to be 200 meters because you're going to go from the bridge down to the ground, and if the bridge is 300 meters high, then your displacement is going to be 300 meters on the down direction, and that's why you have it negative 300 meters. What I want is velocity. The equations we have there are 3 traditional equations, and time is not known, so I can eliminate the 2, and we can use Torricelli's equation again. Okay, so now it just becomes a nice plug and chug, where you need to be careful with the sign, so this here must be positive, because it's up. Now I'm going to have negative 10, negative 300, okay? And then your velocity becomes negative 90 meters per second. Notice that when you take the square root of this whole thing here, you're going to get a positive number. the negative is adjusted. You need to remember that because the object is coming down, that velocity must be negative. Okay? Now let's go up to the next problem, which is the same situation, but now they want to know how long it is in flight, which basically now is an information about time. As usual, I want to ask you to pause the video, work your solution, and come back to see team solution. So now back at team solution, okay, we see the little animation of the ball going up and down. And what do we know? Again, acceleration, negative 10 meters per second squared, which is implicit. Initial velocity to be 50 meters per second, that's given. And the final velocity to be negative 90 meters per second, which, notice, we calculated before. We calculated the previous problem. What we want to know? Time. That's the information we want. The equations we have, the 3 equations in there, and now we need to just think about which one. So we have an equation for time. We want to know time, and we have 2 equations we can use for time. And at this point, we have all of the information because we know acceleration, we know initial velocity, and we also, yes. So we can choose, and just choose the simplest one. Why make our lives more complicated? So the solution then is just going to be v equals u plus at, then negative 90 equals 50 plus negative 10t, and then t equals 14 seconds. So this is the end of this video and of the analysis of team solutions. I hope you guys enjoyed and that's been useful. See you next time.